Assalamualaikum. This video will be a quick revision on sonometer. Let's discuss about sonometer. So we know that in the sonometer experiment, we will have a sonometer wire. We are going to have a sonometer wire. Then we will have a sonometer wire, and in this experiment, the usual procedure is to get a vibrated tuning fork, place it on the sonometer box after vibrating it, and then adjusting the distance between the bridges. We would adjust the distance between the bridges by placing a paper rider on it. Okay, we would place a paper rider and then adjust the separation between the bridges. So at resonance we can observe that the sonometer wire will vibrate with maximum amplitude. Due to this maximum amplitude, the paper rider would jump off. So that's the usual procedure. So when we talk about the procedure, so the first one is to vibrate the tuning fork, and place it on the sonometer box. Then second, what we would do is we would increase the gap between the bridges, right? Bridges or wedges. Okay, and when the paper rider jumps off, we can measure the length. Okay, when the paper rider jumps off, we can measure the length L0. L0. So this is the usual procedure. From here on, depending on what we want to determine, the experiment will continue. Okay, so this is the usual procedure. Now let's look what are the questions that has appeared in the past papers. Based on that, let's make a summary so you can use it when you approach questions. Okay, so let's see what are the questions that has appeared in the past papers. So in 1997 we have had a question. So in the first question, we want to draw a rough sketch showing the variation of y with time. Y is the vertical displacement. So this wire is going to vibrate vertically. Then y is the vertical displacement. We want to draw a rough sketch of the variation with time. We know that this particle is going to execute an SHM. Therefore, it is going to have variation that is similar to an SHM, displacement versus time. Then calculate the periodic time. So if it's an SHM, we know that we can put this into A is equal to minus omega squared x equation. From that we can find omega. Once you know omega, you can find the fundamental frequency, lambda, and so on. Then here, when the students were asked to resonate the sonometer wire using a vibrated tuning fork, they used the following method: holding the tuning fork above the middle of the wire, keeping the tuning fork on the wire, placing the tuning fork on the sonometer box. So which method is correct? So we have to place it on the sonometer box. that is to ensure maximum energy transfer. And then they want to find out what's the minimum displacement of the wire the paper rider will jump off. Okay, so we can apply F equal ma, and from that we can get the answer. So from this question, let me make a summary of what information we can extract. So first of all, when the sonometer is vibrating at fundamental frequency, or when it is vibrating for the first time at resonance, it will be at fundamental frequency. So it's going to vibrate just like that. Let's say the length of the wire is L. Then you already know that velocity of a transverse wave on this wire is given by V is equal to root T over M. From that we also know that at fundamental we have only one segment. We only have one segment here, so lambda naught by 2, that is equal to L. We find that lambda naught is 2L. From that V is equal to F lambda. We can find F is 1 over 2L root T over M. Now these stuff you already know from your theory. One additional thing to add up here, on this wire we have a standing wave. It's a transverse standing wave. When this wire is vibrating, we can hear a sound, the vibration of this wire. So that actually comes through the air, and it's a longitudinal wave. And it's progressive. It's not standing, it's a progressive wave. So it's a progressive longitudinal wave. Now let me summarize what we just checked in 1992. So sorry, 1997. So from the 1997 paper, the information I could extract or summarize was that each particle on the wire executes an SHM. It is executing an SHM. So what we can do is, since it is an SHM, we can use the equation. Since the equation A is equal to minus omega squared x can be used. Okay, so that is what they did in that question. The value of A, omega and x, the relation between them was given. From that we extracted omega. Once omega is known, you can find the time period, you can find the frequency. So that's how that question moved. In addition to that, in the question it was asked how to place the sonometer, how to place the tuning fork on the sonometer. So we have to place it on the sonometer. Box. So if this is the sonometer box, we have to place it on the sonometer and somewhere in between the bridges. Okay, somewhere in between the bridges. So we will place on the sonometer, comma, between the bridges. Don't get confused, it should not be touching. Okay, so Do not touch the wire. So why do we need to place it like this? This is to ensure efficient energy transfer, because the energy now can go through the tuning fork to this bridge and then to the wire. Okay, so it's efficient. Then the sonometer box is also hollow. This is not a solid box, this is a hollow box. Why is it hollow? Once again, to ensure maximum energy transfer, ensure maximum energy transfer, or efficient energy transfer. Efficient energy transfer. Okay. Let's look the next question. So, and here you can apply F equal ma. When you are applying F equal ma, the direction is the direction of displacement. So if you want to apply, or if you want to get the answer for that question, now we know that the paper rider would jump off, somewhere at the maximum. So at this moment, we will have the reaction R upwards, mg acting down. And what is the direction of displacement? It is up. So you have to apply F equal ma in the upward direction. Then we would get R minus mg is equal to ma. If the particle is jumping off or leaving the surface, reaction becomes 0. Therefore, we get A is equal to minus g. But this is SHM, therefore A is equal minus omega squared x, but A is minus g. So now minus and minus cancels. We can find x, it's g upon omega squared. So that is how it's found. Then let's look the question from 2000. A student plans to carry out an experiment using a sonometer to determine the frequency of a tuning fork. Where should he place the sonometer sounder tuning fork in order to obtain resonance? From the sonometer box around the midpoint of the two pegs. What procedure must he follow to obtain the fundamental resonance? So this is a very common question. Then the student measured the fundamental resonance L corresponding to different tensions of the sonometer while using weights mg. Write down an expression relating MLF and mass per unit length of the sonometer wire. So from the equation that we got earlier, in place of tension, we will replace mg. So that those are common questions. Now let's look at question number D. This is a slightly different question. So it's a point note worth noting down. Therefore, let's note it down. Here they say, which of the experimental L values is considered to have highest accuracy? So from 2000, let's note that down. So in 2000, they are talking about the measuring length L. Now we know that to get a higher accuracy, we should have a lower percentage error. We should reduce the percentage error. So how can we reduce the percentage error? What is percentage error? Percentage error is delta L upon L into 100%. So delta L is the least count of the instrument. We cannot do anything with that. Then we have the length L. We could increase it. Okay, if we increase that, then the percentage error will reduce. So if we want to get a better value, then length should be higher. So in that question, what is the experimental L value is considered to have the highest accuracy? The largest value, L value. Give the reason. it has the lowest percentage error in the length measurement. So that's what I said. Now, how to increase the length for a given tuning fork? Let's say you have a tuning fork, then we know that we can get this relation 1 over 2L root T upon M. Now, because it's a given tuning fork, frequency will not change. Given via M will not change. But you want to increase L. To increase L, you only have one option, that is the tension. So let's get the relation. Since everything is constant, if I remove F to M, I get L proportion root T. So if I want to increase the length, if I want to increase the measurement of the length, I can do that by increasing the tension. So if I increase the tension, length for a given measurement will increase. So next question, a graph is plot, then you want to get the gradient, find the frequency. So those are common questions. You can approach it easily. Then 2005. In 2005, the sonometer shown in the diagram consists of two stretched thin metal wires W1 and W2. So this is W1, this is W2. One end of the W1 is attached to a nail A and the other carries a mass M. The pulley P is smooth, W2 is kept under tension by fixing nails R and S. Okay. When W1 is plugged in the middle of BC, the wire vibrates at fundamental frequency. Draw the wave pattern of the wire produced between V and C in the figure shown below. So that's known. How is stationary wave formed? How is a stationary wave of this nature formed? Okay, so to understand how this standing wave is formed, let me show you an animation. How a standing wave is formed. What's a standing wave? So here, standing wave is actually, let me explain that first. 2005. Standing wave is actually two identical waves moving in the opposite direction. Okay, moving in the opposite direction. It may be like this or maybe the other way as well, no problem. Maybe it's like, sorry, it's like this or this. Now it's the same wave. At different times it will look different, right, when it is moving forward a given position. That's what I have shown. So when they are moving in the opposite direction, they will overlap, they will superimpose. So when they superimpose, they create a standing wave. So in a stretched string, we know that if a string is attached to a wall, this is a fixed end. So a pulse that is sent along this wire a pulse that is sent along this wire will undergo hard reflection, therefore it will come from below. Okay, now you know this from wave properties. So the same thing would happen, right? Now just think, in our case our string is tied to the end. Then if you have a wave that is propagating, and this wave would get reflected, a hard reflection. So both of them are identical. Then you have the incident wave and the reflected wave, both of them moving in the opposite direction. So the incident plus the reflected superimpose, creating a standing wave. Okay, so let me show you that animation. Now here, this is our incident wave. This is the incident wave, and this incident wave, consider this y-axis as the reflection point or the wall, so it's going to get reflected. So at this moment, look now. This, yeah, now look, this portion after this y-axis line, you can see that that part is turned around. Okay, it's turned around 180 degrees, and this point and this point looks identical. This wave looks identical to this reflected wave. So these two waves are going to add up. When they add up, this is the wave they produce. The one in green color. So you see that this is the standing wave that you had been drawing all the time. So if it is the fundamental, it's the point between these two. So standing waves can happen in longitudinal wave and transverse wave, but when it comes to so when it comes to this stretch string, we will have only transverse wave, but standing wave is common for both. Okay, standing wave is common for longitudinal waves and longitudinal wave and transverse wave. So in a wire, we are going to have standing transverse wave. So how does a standing wave form? Standing wave is when superposition of incident and reflected wave. So in a stretch wire, we will have transverse standing wave. Okay, transverse standing wave. Let's look at the next question. So superposition of two identical transverse wave of the same speed and wavelength moving in opposite direction. So you can say simply identical waves in opposite direction. Then this is fine. This is fine. This question. The length xy corresponding to the fundamental frequency of vibration of W2 in resonance with the fundamental frequency of W1 is L0. Suggest an experimental procedure to be followed in order to obtain L0. After that, these questions are similar. This can be done. This can be done. So no problem. So let's see what is this question. Now, in this setup, we have two wires. We have wire ABC. Then you have this wire between R and S. So the usual sonometer setup is going to have a tuning fork in place of this wire BC. So look, usually what do we have? Usually we would have this sonometer, then tuning fork, then the sonometer wire and a weight. So this sonometer wire will vibrate. Okay, this sonometer wire will vibrate with fundamental frequency, and you have the tuning fork. What does the tuning fork do? When it vibrates, it's going to resonate this wire. Now in this setup, what we have is, in place of this tuning fork, now if this tuning fork is having frequency F, we would find the corresponding resonating frequency, right? I mean, it will resonate at the similar frequency, then we will find the resonating length L naught. Now in this question, what they have done is they have replaced the tuning fork with another wire. They have replaced the tuning fork with another wire. And um, now if we vibrate this wire, this will produce a vibration at a certain frequency. This will produce a vibration at a certain frequency F. So how would you get the corresponding frequency here? The same procedure. You would put a paper right on top of this, keep the bridges closer, then move it until this paper rider jumps off. So this is the same experiment, no difference. Then from this question, what we can understand, we necessarily do not need a tuning fork. What we need is anything that can produce vibration at a certain frequency. Okay, we need anything that can produce a vibration at a certain frequency. In that case, the remaining rest of the experiment is same. Also in that question, or in that answer, there was another answer. We could use beats to identify resonance. So think, if you are changing this length, you're not changing this length, sorry, you vibrate this, then this has a frequency F. When you are changing this length, without the paper rider, you vibrate this. Then you will have a certain frequency F dash. As you move this bridge, that frequency will keep changing, and if these frequencies are different, we will have beats. When the frequency of both the wires match, no beats. If you move the bridge beyond that, once again beats appear. So that's the second method they have mentioned there. If you want, you can note that also as a point. Then we have a question in 2009. So once again, this is same. All the questions are similar. The only difference is here they are using a different method to tension the wire without just hanging a mass M. Instead, they are using the same mass M but using principle of moments to increase the tension. So you can understand that, no problem. And here they are talking about measuring the simple length, so that can be done by measuring. We can use the equation A rho. So you can measure the diameter. We know that simple M is equal to A rho, and then you can measure the diameter, so that's also not a problem. Then we had a question in 2017. What type of vibration is produced in the surrounding air due to vibration of tuning fork in the experiment? So longitudinal, right? This we already discussed. How to place it, we already discussed. Tuning fork held normal to XY, touching XY. What is XY? Tuning fork held normal to XY with and without touching XY. No, we have to touch it, right? We have to place it on the box. So to transfer energy efficiently. Write down another item normally used is experiment to detect resonance state. Wave rider. Um, we know this, it's usual. So resonance length obtained in the experiment is small. How to adjust this in the above sonometer? So we know that earlier we discussed that L is proportional to root T. So if you tension, length will increase. So you can increase the weight. 2020. In this experiment, fundamental resonance is used. What is the reason? Okay, so we know that in fundamental resonance we will have the maximum amplitude. We have to place the paper rider in the center, that you already know. This is also a common question. What is the tuning fork to be used? Initially, smallest tuning fork, so you will have the highest frequency and lowest resonating length. And now this is a different question, a new one. Vibrated direction of the two prongs of the tuning fork at a given moment is indicated by the arrowhead in the figure. So we want to mark the direction of the vibration of particle in stem S. So for that, look at this. So actually what happens is, when it comes to tuning fork, the tuning forks stem, sorry, these prongs, they actually have transverse wave. Okay, fundamental mode of the average mode. So the question is about the stem, right? So the stem, it would appear that the stem of the fork is stationary. However, the stem actually vibrates up and down at the fundamental frequency as well as second harmonic. So this is a note from a university, so we can take it. Then in 2020, from 2020, we know that the tuning forks prongs, the prongs are having transverse wave. The prongs are having transverse vibration, but the stem, it is having vibration in the up and downward direction, longitudinal. So this is a point worth noting down. Next, maximum length for resonance. Sorry, what is the mass we have to use? So if we increase the mass, then measuring length will increase. If measuring length increase, percentage error will reduce. We already discussed that. And H part, write down a possible error that could happen when determining the resonance length L and the action that you would minimize it. Wave rider jumps off within a small range of length on the wire. Obtain resonance length for a given tuning fork by adjusting the distance between two pegs few times using the above method. Then obtain the average length. So obtaining the average is not a problem. Now this part, wave rider jumping off within a small range. To understand that, let's look at this example. Okay, so this is 2003 resonance tube experiment. In the resonance tube experiment, they wanted to plot the intensity of the tube around resonance length L naught. So here you can see that in and around the resonance length, it is increasing to a maximum and then reducing. Okay, so from this, what idea we can get is that we might think when the length is exactly L naught, when the length is exactly L naught, that is when we have the maximum amplitude. Yes, correct. But in and around, L naught itself, there will be a um, good enough amplitude. Although it's not the maximum, it has a good enough amplitude. Maybe the Pep rider jumps off. Now let's say this is the length we expect, but when the length is over here, somewhere over here or over here, the Pep rider may jump off because it's also high amplitude. Then how can we reduce this? When we take multiple readings, what might happen is, at times it might jump off here, at times it might jump off here, it might jump off here. So when we take a few readings and get the average, then we can get a better value for resonating length L naught. So that is what it is mentioned. So better mention this also in the note. So what we can say, the paper rider may jump off for lengths or for a small range of length around resonance. Okay, around resonance. So how can we reduce the error? By taking average, for average of multiple values. For L, this could be reduced. This error could be reduced. Now, so in 2020 only we had the last Sonometer problem. Let's look at this revision paper as well. So the questions are very common. Where should he place the vibrating tuning fork to obtain resonance? On the sonometer box, somewhere in between the bridges. So draw the appropriate place to place the sonometer. So in the center, what is the practical procedure that must be followed by the student to obtain fundamental resonance of the sonometer wire with the placed tuning fork? So the usual answer. Which tuning fork should be used first to ensure the resonance can be obtained for all the tuning fork in the given set? Now this is slightly opposite to the normal. Usually we take the highest frequency to get the lowest length. But here they want to ensure all the tuning forks will have resonance. Therefore it's the opposite, right? We have to take the lowest frequency to get the highest length, then whatever below that will have resonance. If resonance cannot be obtained for a particular tuning fork, what change should be done by the student in the sonometer? So once again, this is opposite to the normal. We know that L is proportional to root of T. Now why he is not able to take reading? Because maybe the resonating length is more than the possible length for the wire. So he want to reduce the resonating length. How he can do that? By reducing the tension. So he can reduce the tension by reducing the weight on the wire or the load on the wire. What is the practical procedure used to reduce error caused due to uncertainty in obtaining resonance state? So that is what we discussed finally, right? We can take multiple values and get the average. Write the equation that's normal. Um, Here you have to subject y without having inverse. So we know that f is 1 over 2l root t over m. So take L to that side because L is the dependent variable, and L is the dependent variable and 1 over f is the independent variable. Draw the rough sketch. So this is in the form y is equal to mx, therefore 1 over f L. This is the graph. Mark the fundamental resonance L naught of the tuning fork of unknown frequency is measured. So we have measured the unknown frequencies tuning fork and it's L naught. Then we want to find F naught. So if this is L naught, then here it will be 1 over F naught. Okay, so we can find 1 over F naught. From there we can find F naught. That's all about sonometer. So I hope this summary would help you all a lot. Assalamu alaikum.